In this video, we present the highlights of our paper, Embodied RAG, General Non-parametric Embodied Memory for Retrieval and Generation. Our research explores whether we can create an embodied agent that memorize and understand the environment, able to use this knowledge to interact with people with natural language. This allows the robot to be used, for example, help a visually impaired person navigating the city, creating risk analysis reports for a search and rescue task, or chat with a golf manager about the grass condition today on the golf course. From previous research, we observed that deploying large language model as embodied agents works well for open vocabulary question answering and zero-shot navigation by iteratively prompting the large language model in a Markovian manner. However, this approach fails in several ways. First, they only work in small environments. Since large language models have a limited context window, they can only partially observe a large environment in context. Second, this method fails to understand the environment holistically, as their context is limited to what the large language model agent perceives at the current time frame. Third, they are inefficient. To navigate a large environment, they require constant large language model calls at each time step. Fourth, they operate solely on image data without utilizing other modalities. Therefore, we argue that a multimodal, globally aware memory should exist for large language models as embodied agents. However, matrix maps, such as 3D point cloud maps, traditionally used as robotics memory over environments, are difficult for a large language model to directly use because they lack semantic data. Semantic maps are often used by learning-based agents to navigate environments, but they are not generalizable to open vocabulary scenarios and are not easily accessible for a large language model to retrieve information from. In the NLP community, retrieval augmented generation is widely used to enable large language models to access real-time, large-scale, and domain-specific data. This is achieved by breaking custom documents into smaller text chunks, generating embeddings, and storing them in a vector database to augment the large language model's context during generation. However, there are several challenges in directly applying RAG to embodied settings. First of all, embodied data is fundamentally different from internet text data. It is often multimodal, containing information such as locations and various sensor data, including depth, lidar, temperature, or humidity. These data are typically represented as tuples along the time dimension. Second, embodied questions necessitate a versatile embodied retrieval mechanism that can effectively utilize different types of input data. Questions like find the closest object requires the query to have locations as input too. Third, embodied generation should go beyond producing text. It should be capable of generating actions too, such as waypoints or paths. This led to our research, Embodied RAG. The proposed method begins by collecting multimodal trajectories and logging them into a topological graph, where the nodes contain information such as time, locations, and sensor data, and the edges represent traversable paths between the nodes. Next, we construct a semantic forest from the bottom up by hierarchically clustering the nodes, generating area summaries until no further clusters can be formed. For retrieval, we use this semantic forest to respond to user queries given in natural language format. This context window is populated with the retrieved multimodal nodes, enabling generation of either natural language text or waypoints, depending on user's request. This is a detailed breakdown of our method. We cluster the nodes based on spatial and semantic proximity, automatically generating area summaries by querying large language models in parallel until constructing a hierarchical tree. To traverse the tree, we use a large language model-based selector that identifies top k child nodes to explore, starting from the root. Once the context window is populated, we remove the duplicated nodes and re-rank them based on query's location and other available sensory data. Finally, the selected nodes are fed into the large language model for generation. We collected 14 different embodied experiences from different sources, from real robot trajectories to a realistic Unreal Engine-based simulator aerosim to log Google Street View images. For each environment, we collected 3 different types of queries, in total of 250 queries over 14 different topological graphs, and created the embodied experience dataset, also available for future researchers to test their embodied RAG method on. Here is the result on human asking the suggestions for a drink.
I'm dehydrated. Can you take me somewhere?
The goal is to find a place to help with dehydration. Among the nodes described, node 102 is the most relevant as it contains a beverage vending machine, which includes a bottle of Aquafina water. This directly aligns with the need to find a source of hydration.
We benchmarked our embodied experience dataset with 3 baselines: naive RAG, graph RAG, and lat RAG. We see embodied RAG outperform the baselines by a large amount on explicit and implicit queries, and achieve similar and higher result on answering global level questions. We also see that the memory building time of embodied RAG is much less than other graphical RAG baselines, since we cluster the nodes using spatial proximity other than excessively calling large language models to cluster and extract relationships from the text chunks. This makes embodied RAG can be deployed in real applications such as search and residues. Thank you for reading our paper, and for more details, please refer to our website for dataset and query examples.